Hello everybody, and welcome to Ask Math Anything. It's good to see everyone again, and if you're new here, if you're here for the first time, I want to welcome you to a show which is not exactly like a math class. Actually, this particular math class is a math class where it's all based on your questions. I didn't design anything to teach you in advance, so that we could find out what people actually want to see today. If you're new here, you will also notice that the style of this is actually very fluid, in the sense that we always go and look and see what kind of questions we might be able to use to tell an interesting mathematical story. I know that many people who are here are taking algebra or geometry, and so what we'll always try to do is we'll try to choose some questions that we can explain in a level that's understandable to people who are taking algebra or geometry. Although we'll usually actually end up going quite deep and talking about things that you wouldn't see in your algebra or geometry class. So if you're new here, welcome. If you're not new here, I have a way that I can tell, which is that everybody seems to be talking about the haircut or the color of the shirt. Yes, I did actually finally get a haircut last night. And yes, I hope that this is a little bit more presentable. I decided I couldn't just wait until the end of the quarantine to get a haircut, or else my hair would be a big mess. All right, there's the first question of the day. How did you get a haircut? Somebody at home helped me to cut the hair. I don't know how to cut my own hair. You know, there's one of these jokes here, which is that if the barber cuts everyone's hair, if the barber of Seville is the one that cuts everybody's hair, who cuts the barber's hair? All right, let's start talking about some of these questions. What can we talk about today? Usually what we'll try to find is some interesting mathematical problem that we can discuss. Oh, somebody's asking if the sound is quieter than usual. Let me double check. What do we have here? No, that one seems fine. It seems fine. Maybe I'm just not talking as loud as I usually do. Okay, great. What kind of questions can we discuss today? Let's see. So we're looking at all of these different questions. Okay. So I'm just looking at all of these to see somebody is saying area of an equilateral triangle. Okay, let's talk about that. Area of an equilateral triangle. Now, this is something which has a formula, but I want to talk about area of an equilateral triangle for a different reason, okay? And this will give you an example of what we usually do in this live stream if you've never been here before. We start with something that might at first be quite standard, and we use it to talk about something that's not so standard, okay? So the question was area of an equilateral triangle. Okay, so I think I need to draw an equilateral triangle for you. And if this is an equilateral triangle, oftentimes the way you'll come up with a formula for the area is that you'll have a letter called S, and S means the length of a side. S, S, and S, okay? Oh, I have an idea. I don't want to call it S, and you'll see why. I want to call it X. Okay, we'll call it X just for fun. Now, if I want to go and find the area of the equilateral triangle, I need to use a formula. Who knows a good formula for the area of a triangle? What should I use? What kind of formulas could I use for the area of a triangle? I think there's one which is quite standard, one that's very easy to use. Haha, so somebody already has thought of what I want to do. We're going to do half base times height first. Someone said this looks kind of like a face. You guys have a good imagination. All right, so now let's try to cut this thing in half to make a height. And the way that you do this is an equilateral triangle. That means it's very symmetrical. So if x is the whole base, then each of these is half of x. So let me erase this x. Each of these is x over 2. Now, if each of these is x over 2, I could use the Pythagorean theorem to go and figure out what that is, right? That's an x over 2. So what is this? If you have done this before, you in fact even recognize what it is. But if I was slow, I could even go and do it slowly. I could go and say that this happens to be, by the Pythagorean theorem, square root of x squared minus x over 2 whole thing squared. And that's equal to square root of 3/4 x squared, which is equal to, if I simplify, x over 2 root 3. And indeed, it's a common trick whenever you have an equilateral triangle, that whatever this is, this thing you multiply by root 3. But if you forgot, no problem, you can do this. And some people like Willow the Pillow are saying, I know this. Yes, this is actually something that many people will learn in math contests or in algebra class or maybe geometry class. Let's do it now. Half base times height. Here's half the base, x over 2. The height is x over 2 root 3. So when I multiply them, the area is equal to half base times the height, which is equal to x over 2 times x over 2 square root of 3, which is equal to x squared over 4 square root 3. So that's the formula. So that's the formula for the area of the equilateral triangle. But I wanted to do something else with this. And oh wow, I like things so that you learned that from me. I guess maybe you took our class. Well, nice to see this covered again. But now let's talk about something you could use this for. You see, I'm going to think about baking cookies. And I'm going to think about baking cookies where I want to put as many cookies on the pan as I can. And if you want to put a lot of cookies on the pan, we've already talked about this on a live stream. You'd want to put the cookies on the pan in this kind of a pattern. Does someone know what I'm going to do? Somehow this is slanted and going up to the right. But I'm doing this, right? I'm just putting all of these lumps or these cookies on the pan. And it's not in a nice square grid shape. It's in these hexagon beehive shape. So this is one way that you could make lots of cookies. Do you agree? I could make lots of cookies by just taking these cookies and putting them on the pan. Does anyone know why we don't put them quite this way? If you've ever baked cookies before, I think cookies kind of get bigger as they start baking, so they would always like smush into each other. But there's another way to do this. Another way to make round cookies is just to make a big sheet of cookies and then just cut them out afterwards. All right? So what I'm talking about is, gee, I wonder what fraction of the pan is used up this way. I see someone already put in the answer, but I want to talk about how you'd figure this out. Suppose you had tons and tons and tons of cookies. What if I wanted to know what fraction of the space used by cookies? Maybe I shouldn't call it space, I should call it the area. Even though cookies are three-dimensional, but let's just do it this way. Fraction of the area, and indeed, we should connect. Oh, somebody said this was in his module 2. I guess this is something that's actually in our online class. But this also shows this is an example I love, right? If I wanted to know what fraction of the area there is, you would connect the centers. And you'd simply say that I actually happen to have inside this equilateral triangle, like what fraction of the space what fraction of the area do I happen to cover up? And since the whole baking sheet is made by tiling these one next to each other, I only need to know what the fraction is in one of these. So if you wanted to know, this is where we could then use the formula for the area of a triangle. Because if I want to know what fraction of the area of this triangle is covered up by this, now I can actually figure it out. Because if the side was x, then I know the radius of the circle. The radius of the circle is half x. So this part here is x over 2. Here is another x over 2. And let's make the x over 2 more readable. X over 2 like this. So x over 2. And I could use this to go and figure out what is the actual part that's shaded in. What is that? I have 3 little pieces shaded in. How much of a circle do they add up to? If I have these 3 sections of the circle, if I put them all together, how much of a circle is that, the blue stuff? Half the circle, right? Because each of them is 1/6 of the circle. Put 3 of them together, it's 3/6, so it's 1/2. So that means that somehow the blue area is equal to 1/2 times pi times the radius squared. And I would divide that by the area of the entire triangle. Which is equal to x squared over 4 times the square root of 3. And now you just cancel the x squared, because both of them have an x squared. And if we cancel, we get some funny number. This is equal to, what is it? It's like pi over 8 divided by root 3 over 4. Does anyone know what this is? At this point, it's not easy to do this without a calculator. So is there someone here who has a calculator who can help to figure out what is pi over 8 over root 3 over 4. I guess I can simplify that. While people are taking out their calculators, if I multiply the top and the bottom both by 8, then I get pi over 2 root 3. And while people are doing this with the calculator, 2 root 3 is 1.732. 2 root 3 is like 3.4 something. So it's like 3.14 over 3.4. That's quite nice. Actually, that's almost 100%. That's 0.9069. So 91%. So the area of an equilateral triangle is useful. You can use it to figure out how much of your baking sheet you cover with cookies if you use the beehive pattern. Great. And another thing I want to say about this area of a triangle, you could do it this way, but some people also suggested using Heron's formula. Why not? There's another formula called Heron's formula. Heron's formula. Now, I don't have the time to prove this on this short live stream here. That one we actually did in our class too. But Heron's formula is that the area is equal to the square root of, it's pretty long, s times s minus a times s minus b times s minus c, where s is the semi-perimeter. S is equal to a plus b plus c over 2. And now you see why I didn't want to call s the side length. Because for the side length, I wanted to use x so I could save the s here. That's actually the reason why I wanted to do this. So if a, b, and c are all x, then the semi-perimeter is 3x over 2. And so the area is just the square root of 3x over 2 times s minus a. A, b, and c are all x. So if I take 3x over 2 minus an x, then it's just x over 2, x over 2, and x over 2. And if I simplify that, then I get x squared, and it's divided by 4, square root 3. And that's another way to do this. Okay, so this is, by the way, not the recommended way to find the area of an equilateral triangle. This is massive, massive overkill because we've just used something way too complicated in order to find the area of a very simple object. But it's always fun to see that such things are possible. Okay, more questions. What else can we do here? Let me first clear my screen. For some reason, one of the problems is, so I have multiple computers here. One of them, two of the computers use Linux. One of them uses Windows. And the Windows computer just decided to start scanning for viruses. So hopefully I can still see your, I hopefully can still see your comments even while it's scanning. So let's see, what can we do here? Ooh. So I see an interesting question by Mohammed Al-Majid, who said, hello, in how many ways can we arrange a 6-digit number such that it is non-decreasing? I'm not really sure I understand your question, because if I want to rearrange a 6-digit number to be non-decreasing, I think I would just sort the digits in order from small to big, and then the answer would be 1. It seems like there's only one way. So I think we don't completely understand your question as stated, but maybe you can restate the question and we'll try to find it. What else do we have here? Oh, Andrew Chow. Are there more irrational numbers or rational numbers? This is a famous thing, which is very interesting. All right? So the question is, which is more? Rational or irrational? Now this is kind of complicated because both of them, they're infinitely many, right? And by the way, if I have any rational number, I can tell you how I can make an irrational number. I just take the rational number and I add pi. So for every rational number in the world, I can go and make an irrational number, right? So that seems like irrational numbers might be more. But in order to really do this properly, what you need to use is you need to use the notion of what's called one-to-one correspondence. You need to be able to say, look, how many rational numbers are there anyway? The easiest way to look at this is to first show that the number of rational numbers is the same as the number of positive integers. That's the first step. To show the number of rational numbers is the same as the number of positive integers. So first, the number of rationals is equal to the number of positive integers. Okay, and so how would we go about doing this? We basically just need to show that there's a way to give each rational number an ID, and that ID should be a different positive integer. And if I could give each one of those a name tag, then I guess they have the same number, right? Because I could just imagine I have all my rational numbers in the world, and each one has a name tag saying, I am rational number 327. And if every single person gets a different name tag, and I use all of the name tags once, then it's the same number. And here's how you do the name tags, okay? First I do it for, well, we can do it for positives and negatives separately, okay? So first I'm going to do it for the number of positive rationals. The way you do this is you go and write down your rational numbers like this. Positive rationals would be like 1 over 1, 1 over 2, 1 over 3, 1 over 4, 1 over 5. Here's all these rational numbers. If I go like this, I can write down all the rational numbers in the world. 2 over 1, 2 over 2, 2 over 3, 2 over 4, 3 over 1, 3 over 2, 3 over 3, 3 over 4. I'm getting lazy. So I just write down all of these. Now let me tell you, here's how I'm going to make all the name tags, okay? I will say that this person here, the 1 over 1, got the name tag 1. Okay? So this guy here has the name tag 1. This guy here has the name tag 2. This guy here has the name tag 3. This guy here has the name tag 4. And I just keep going. And when I'm done giving all of them name tags, then I give the next one the next name tag. Oh, this breaks. The reason this breaks is, what do you mean you keep on going? You'll never finish. So you'll never give a name tag to this person. This person will not be happy. Temp ID says there might be duplicates. We're going to deal with that soon. But I'm first showing why you can't just go and give name tags like this, or else you just never get to everyone else, right? That just doesn't work. So let's change the strategy. Instead, we'll give that one a 1, give that a 2, and then we'll diagonal down here. And we'll give this one name tag 3. Then we give this person name tag 4. And then this person, we say, we already saw that fraction. It's a imposter. We don't need to worry about it. It's one of these duplicate IDs. Ignore that person. So then we go over here, and then this one we'll call name tag 5. Okay? So now let's just keep going. I guess this person will be called 6. You see what I'm doing? I'm just going diagonally. I'm just going diagonally, 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 like this. The next one, let's give this person name tag 6. This person gets name tag 7. This is name tag 8. This is name tag 9, the thing that's here. 10 is over here. 11, it's an imposter. We've seen it before. Actually, this 3 over 3, we've seen that before too. And then we'll have seen this 4 over 2. And finally, this is 11. What I'm showing you is I can go and give all of these name tags, right? And if I gave all these name tags, all of the positive rational numbers would get name tags. And now if I did that with all of the positive rational numbers, I can also do that for all the negative rational numbers and the positive ones at the same time by just being fair, by saying, all right, when I'm giving out name tags, I first give it to the positive one, and then I give it to the next negative one, and then the next positive one, and then the next negative one, and the next positive one, and the next negative one. And every single person who's not an imposter will eventually get a name tag. So that's why the number of rational numbers is the same as the number of positive integers. This is a very important point. Okay? So this in fact works even without the word positive. Now, the next thing that we need to do with this is we need to say, in that case, I'm comparing how many positive integers are there against how many irrational numbers are there. And here's how you go and show that there are more irrational numbers than positive integers. And this is the most, one of the most beautiful things I'd ever seen in terms of a math proof when I was learning math at the beginning, like learning proof math at the beginning. Okay? It goes like this. Like we'll use reddish color to indicate that we're about to assume for the sake of contradiction. Assume for contradiction. Well, let's write the whole word. Assume for the sake of contradiction that it's possible to give these positive integer name tags to every irrational number. it's possible to give name tags 1, 2, ... to, oh, that's strange. It looks like my pen just stopped. One moment, please, while we do the usual of restarting the drawing program. One moment, please. Great. Okay. This is why I use Linux. All right, let's keep going. So now what we were just saying over here was assume for the sake of contradiction, right? Assume for the sake of contradiction that it's possible to give name tags 1, 2, 3, ... to all irrational numbers. Okay, now suppose that's possible. Well, then let's look at what it looks like. Here, look. Here is the irrational number 1. And what is it? I think I just love pi, right? So the first irrational number was 3.1415926. I sort of forgot. There's more stuff, okay? The next one I make, the second irrational number that I want to list, another of my favorites, 2.718281828459045, and I don't know any more digits. That's E. And let's write down another irrational number. What if it's 4? It's not 4, it's 3. It's 1.414 something, which I forgot. It's the square root of 2, okay? So I write down all of these irrational numbers, and let's pretend that we've got them. We've got this whole list that goes forever. Now here's what we do. We're going to make a new number just for fun. Here's a new number. The new number looks like this, 0. The first thing I do is I go and take the first digit after the decimal point, that's this 1, and I choose any digit other than 1. Well, specifically, I take the digit after 1, and if I have 9, I round up, I go over to 0, okay? So the digit after 1 is 2. And the next thing I do is I go to the second number, and I take that digit, the second digit after the decimal point, and I go to the next digit after that. After 1 is, oh, it's 2 again. Won't always be 2. Take the next one, the third one. For my third digit after the decimal point here, I'm going to take the third digit after the decimal point there and shift it by 1 also. 4 becomes 5. Does everyone understand what I'm doing? What I'm doing is I'm saying I've got this big list, and they are the numbers with name tags 1, 2, 3, 4 forever. And C++ robotics says that this is George Cantor's diagonalization argument. Because we're doing the diagonal, we're looking at the diagonal, and we're making a new number. And that new number happens to be 0. We'll always start with 0, and then we'll look after the decimal point, and we'll always choose like the next digit, the next digit, the next digit. Now, if I did this, guess what? I will be able to build a number, because I'll be able to tell you all the digits of the number, but this number is not in the list. Why? Why is this not in the list? Well, what if somebody told you, it's in the list, this number is the 5 millionth number in the list? Then I go to the 5 millionth number in the list, I look at the 5 millionth digit after the decimal point. Oh, and when I made this, I made sure they were different. Do you see this? This number that's here happens to be different from every single number in this list at least one decimal place. Because there's at least one decimal place where we were just making sure, just screwing it up for fun, where we said that's the 4, nah, we're going to make a 5, right? So what we have here is we actually are able to avoid all of the numbers that we've seen. And so now we've gotten a contradiction. This number here is not in the list. And if it's not in the list, then it just can't be. We've just got a contradiction. This list is not complete. Okay, so this is the proof that you'll usually hear about. If you want to make it a little bit more rigorous, a faker, that's right. This is a faker. Or rather, if somebody who told you it was possible was lying. But something I should say, there is a deal where you have to worry a little bit about whether or not you have repeating decimals of like 0.99999 being the same as 0. But something that helps is that if I write down a lot of irrational numbers, there are no irrational numbers which happen to have repeating decimals that go forever. So actually every one of these numbers is unique. All right. Well, that was a fun question about what are there more of, rational numbers or irrational numbers. The answer is irrational numbers there are more of, because the number of rational numbers is the same as the number of positive integers. I could list them all. I could list all the rational numbers if I wanted to, but I can't list all of the irrational numbers. More questions. What do we have here? Wow. So many questions. Somebody asked, how do you prove Heron's formula? The easiest proof I know uses the Pythagorean theorem. Use that as a fun challenge. You basically need to go and take your ABC triangle, put in some variables and put in h for the height, and write down some equations that use the height h and the x, which is sort of like where the height hits the base of this triangle. Once you write down this thing, you can solve with a system of equations and you'll get Heron's formula. And I actually did that at some point for a class that we were teaching, but I won't do that here because it took like half an hour. Okay. Oh, Colin Z. Are there more composite numbers or prime numbers? Ah, I like that question too. So we seem to be talking about numbers and how many of different things there are. So let's write down this question, okay? Question by Colin Z. Which has more? The number of primes or the number of composites? Okay, what do people think? So this is a very funny question, okay? Because you see, this thing intuitively, the answer seems to be one way. For example, if someone asked you, what are there more of? Positive integers or positive even integers? You might say there's obviously more positive integers. I mean, I'll tell you a positive integer that's not a positive even integer. 5, right? 5 is a positive integer and it's not counted in the positive even integers. So we should probably have been a little bit careful about this word more also. Because effectively we're comparing two infinities. So mathematically, what we're going to do is we're going to say, is there a way to make like a correspondence between, like a name tagging between between each prime number and each composite number? And the answer is actually yes, there is. And that's because the number of each of those is the same as the number of positive integers. And so, therefore, there's the same number of primes and composites as well. This is because these numbers aren't like numbers like 50. Like when I say how many are there, I'm not saying there are 50 of them. These are things like there's a certain notion of infinity, right? So the way that we're going to answer this question is we're going to show that the number of primes is in one-to-one correspondence with the number of positive integers, and the number of positive integers is in one-to-one correspondence with the number of composites. And so if there's the same, if I can give a positive integer name tag to every prime and use every name tag exactly once, and I can also do the same for composites, then the number of primes and composites can also be linked to each other. Yes, this is something that a lot of times when you look at it, it's like, wait, how could two infinities be the same? Effectively, what we have just done is we've just proved that there are two different kinds of infinities. That's what we just did with the rational numbers and the irrational numbers. They were different kinds of infinities, and the irrational numbers were a bigger type of infinity. Now here, we're going to compare two kinds of infinities, but these two infinities will be the same infinity, because there is a prime with a name tag 56. And there's also a composite with a name tag 56. So I could say that those two are like long-lost twins or something like that. Like some prime number and their partner composite, just based on what their name tag is. But there's going to be a way to give a name tag to every prime and a name tag to every composite. And how? The way you can do this is that, look, what are the primes? The first thing is there are infinitely many primes. That's a really neat proof. But there are infinitely many primes. The primes are 2, 3, 5, 7, not 9, 11, 13, and so on. You know how I'd give a name tag to each prime number? I would just go and say, this is number 1, this is number 2, this is number 3, this is number 4, and so on. And I'll actually get to every single prime number. I'll get to every single prime number because I don't have this issue where in the rational numbers, I kind of went forever here and then wanted to start here after I was done already going forever. You can never be done going forever. But if you just say like, yeah, we'll go and go and go, and everyone will get a name tag, that's okay. Every prime gets a name tag. You know how I give name tags to composites? The same way. For the composites, what in the world did I just write? I was trying to write composites. Okay, composites, 4. Wow, it's a lot harder for me to write the composite numbers for some reason. I'm so used to writing prime numbers, but I'm not really used to writing composite numbers. It's almost like saying a tongue twister. I hope I didn't miss any. But now let's give them their labels. Number 1, number 2, number 3, number 4, number 5, number 6. You see, the only important thing here is that I am actually able to get to every prime eventually, because if I have a prime like, what's a nice big prime? Is 1001 prime? No. Is that 7 times 11 times 13? Is that right? So 1001 is not prime. So what's a nice prime? 1003, is that prime? Let's pretend 1003 is prime. I don't actually know off the top of my head. But suppose 1003 is prime. At some point, I'll give it a name tag, because I'm just kind of marching along, and I'll eventually get to 1003. And I'll be like, yep, you got a name. And so because all of these primes and all of these composites are all actually in the positive integers, eventually I'll count to them. All right? So that's how I could say, here's my correspondence. You see, this prime number 7, their name tag is 4. And their long-lost twin is 9 in the composite world. And so there's the same number of them, because I can link them all together. I can match them all up. You might ask, hang on a second, then can't I use this method to give every real number a name? You know, just go through all the real numbers in order and just say the first real number is name tag 1. The second real number is name tag 2. There's only one problem. What's the smallest non-zero real number? I mean, okay, I could say that 0 is a nice real number. Give him name tag 1. Now, what's the next smallest? What's the next smallest real number that's not 0? Like the next smallest, well, you just can't. I mean, it's not like 0.00000000000. Like, where do you stop? You know what I mean? It just doesn't work. But over here, with the integers, you actually can stop. You can say, well, it's 2, and then it's 3, and then it's 5. Okay. So this is how this works. So I guess today we're having a lot of fun talking about different kinds of infinities. What other questions do we have here? Oh, let's finish this off. Willow the pillow, is 0 prime or composite? To be honest, I don't really know whether I would call it composite. I will tell you it's definitely not prime. Okay, and this is one of these things where it's like the definition, I myself am not really big on just the definition for the sake of a definition. I'm interested in things for the purpose of what they can be used for. But my instinct is to say neither for a certain reason. So it's not prime for sure. The prime numbers are numbers that you use to build other numbers by multiplying. And that's, by the way, why 1 is not a prime number, because 1 is kind of useless for multiplying in to build another number. So 1's not prime. And 0 is really useless for building another number by multiplying, because what happens if you multiply by 0? Oops, 0. Or rather, if you're doing a math competition and it's some kind of a mental math problem, you just hope that somewhere in that mental math problem there's a times 0. Okay, so 0 somehow is definitely not prime. Is 0 composite or not, I already forgot what people teach in school nowadays. So I'll trust your teacher on that one. I'll simply say that 0 is not a number that you can make as an ingredient for multiplying other numbers together. Oh, you know what? This made me think of a really fun problem. Okay, here's a problem that I saw when I was doing math contests in school. The problem was like this. Have you ever seen these alphabet type things where you say A equals 1, B equals 2, C equals 3, all the way to Z equals 26? Okay, so let's pretend we got all of these. And now, here's a really neat question. The question said, figure out what happens if you do A minus X times B minus X times C minus X times all the way to Z minus X. Does anyone know what the answer is? Hopefully you're good at calculating factorials. Oh, you guys got it right away. So this thing happens to have x minus x inside it. So there's an x minus x over here. That's 0. And since it's 0, poof, the whole thing is 0. So this was a question that was on the Math Counts Countdown round, I think in the middle of the 1990s. And I remember when I first saw this, I think it was on the screen. We used overhead projectors back then, not computer projectors. But I saw this on the screen, and this popped on the screen, and immediately someone went, bzzz, and they said 0. And the whole room gasped, because everyone was like, what? How did you calculate this so fast? I mean, sorry, the person buzzed, and everyone's like, what? And then finally the person says 0. And then you can hear the room say, oh, that's what happened, because there was a 0. Because otherwise you look at this and you say, do I need to do like 26 factorial or something? Okay. Oh no, you want to mess it up? So now somebody is giving me a different question. A minus x times b minus x all the way to w minus x, and skip the x minus x. Then it's painful. And we won't do that here. That's just a computation for the sake of computation. Okay, more questions. What else do we have? Oh, interesting. Okay, let's do something that's about like a learning math piece, okay? So we have a question from David Henry Jones, which is, what is your key piece of advice for succeeding in calculus or any complex mathematics study? The key piece of advice is just make sure that you have enough time to digest what's going on. You asked about complex mathematical study. I mean, some kinds of things that people learn are relatively quick things, but sometimes they're conceptually more complex. So what I did whenever I was trying to learn a complex thing is I would actually go and read, when I read a textbook or when someone teaches me something, they would tell me, here's a method, or here's a fact. And what I would say is, that's nice. I wonder if I can figure out that fact for myself. I wonder if I can explain to myself why that fact is true. And I'll just go and sit down with a paper and a pen and just kind of try to figure out, why does this Heron's formula work? Or why does this formula about calculus, the integral, why does it do what it's supposed to do? And if you go and sit down and yourself convince yourself of why these things work, if you do that, then all of these complex subjects become not complex. In fact, that's why I'm comfortable running these live streams with you guys. Whatever you ask, if you ask me questions and I don't know the answers, you're just watching me do what I was doing when I was trying to learn the complex mathematical subjects. I would just learn that, oh, this is supposed to be a true fact. I wonder why. Let's try to find out. And after a while, you'll be able to solve all of these complex questions because you just understand how to think about that subject. Somebody has asked the question, do I have a floating keyboard? I mean, I guess I could make the keyboard float. Yes, the answer is I do have a floating keyboard over here. But the reason I have the floating keyboard is because that's how I draw on the tablet. I mean, if you've noticed, when I had to restart the computer or restart the program, this is basically a tablet that I can draw on, which has no keyboard. So if I need to have a keyboard, I need to have another keyboard which is plugged into it somehow. Okay, more questions. Oh, okay. Xiao Chu Cheng asked, what is the probability of getting a perfect score on the SAT by guessing every question? Here's what I'll say. The answer is extremely low because we did something very similar yesterday, or I think it was yesterday, where we said, what if you randomly guess every question? What's the chance you get? 0. Actually, that's also very low. And the way that you would think about this is that when you randomly guess, you have a 4/5 chance. I think it's 5 choices. So 4/5 chance of getting each one wrong. And so, we do it the other way around. If you want to get a perfect score, it's 1/5 chance of getting right, and you take 1/5 times 1/5 times 1/5 for every one of the problems you're doing, all the way until you have all the problems, and so you have 1/5 to the huge power. So it won't work. Now, if you try to do this on the AP exam in high school, it's even harder. And that's because the AP exam has free response questions. And I mean, how do you randomly guess on a free response question? Like, what would you do? What does guess mean if you have to write down a paragraph? What do? Just like draw a cat or something? I'm not really sure what a random guess would mean. But if you did that, that's a 0 right away. So free response questions are very, very hard to guess on. Okay. More questions. Oh yes, randomly typed letters. Bob the cat has appeared again, I guess. Okay, what else can we do? I'm trying to find something that I can use to maybe discuss something which, I mean, actually we've been talking about a lot of math so far, but I'm looking for something more concrete. Right, we've just talked a lot about abstract math today with these like infinities. I want to find something which is a concrete problem, which is also kind of interesting that we can discuss. I'm looking at this carefully to try to understand what these questions are even asking. Oh, this is cute. I wonder if I know the answer. I mean, I wonder if I can figure this out. Hopefully this is not too hard. If it's too hard, then we'll say, sorry, it's too hard for this audience we have. But so this is a question by Dudruf the Legend. And Dudruf the Legend asked, how can we find the radius of 3 circles where the circles look like this? Always draw the circles first. So here are 3 circles. The circles don't have the same radius. Let's pretend that those are circles. And now you see why I said draw the circles first, because there's supposed to be a triangle too. So now we draw a triangle. You connect the centers of the circles. Wow, this actually looks sort of legit. All right, so I connected the centers. Lumps, it looks like lumps. So now I've got this. Where did it go? Now the triangle sides are 16, 18, and 20. So this one is 16. This one is 18. And this one is 20. And the question is, what are the radii of the 3 circles? I like this because at first it looks like it's some geometry problem. Oh my goodness, it must be really hard. Some geometry problem that has circles, it has a triangle. It must be too hard for us to do. So maybe we should give up. Or not. Actually, once you draw a diagram carefully, we decide we have to solve some equations, right? So this can't be that bad, because if I have these circles, they have some radii. Temp ID has an idea of using algebra. Let's suppose that the radius of this circle is x. And let's suppose that the radius of this circle is y. And let's suppose that the radius of this circle is z. Oh boy, maybe you've seen this before. This is like 3 unknowns, x, y, and z, and I know the sums of the pairs of the unknowns. Okay, so I happen to know that the pairs of the unknowns, x plus y, is 16. Okay, but you see, I like this because I can also tell you something about geometry. Do you know what's the semi-perimeter of this triangle? We already saw semi-perimeter earlier in today's live stream. What's the semi-perimeter? Well, the semi-perimeter is exactly half of the perimeter. But look, there's 2 x's, 2 y's, and 2 z's. No, 2 x's, 2 y's, and 2 z's inside this triangle. So half of that will just be an x plus a y plus a z. That's very convenient. Because if I just can tell you the semi-perimeter of the triangle, I could figure out what z is. See this x here? If I want to know what z is, I just take the semi-perimeter minus x plus y. Wait, this is x. If I want to know what x is, I take x plus y plus z minus the y plus z. But I know y plus z. Y plus z is 20. So this is how you can look at the picture and even solve the equations without writing them down. Because I know what the semi-perimeter is. It's half of the legit perimeter. 16 plus 18 plus 20, right? So the semi-perimeter, on the other hand, is also 16 plus 18 plus 20 over 2. What's the fastest way to add 16 plus 18 plus 20 over 2? I'll give you a way I usually do it. I see that, you could just halve them. You could say 8 plus 9 plus 10. Actually, that's not bad. I'll do it that way. It's 8 plus 9 plus 10. The reason I say I'll do it that way is whenever I add up 3 numbers which are equally spaced, I just triple the number in the middle, because that's the average. So 8 plus 9 plus 10, they're equally spaced around 9, so it should be the same as 9 plus 9 plus 9, which is 27. This is how I minimize mistakes. If you want to minimize mistakes, don't just do like adding and carrying. It's too easy to get it wrong. But it's a lot easier to say, I'm multiplying. And I know that 9 times 3 is not 37. It's just not in my head. My head knows what 9 times 3 is. It would say 37. That doesn't show up in the multiplication table. But if you do things by adding, you would never know that you're trying to get something staying in the multiplication table. So that's my double check. Okay, 27 is x plus y plus z. So what's x? X is just the 27 minus the y plus z. The y plus z is 20. So if I take this, I can find out that the x is equal to semi-perimeter minus y plus z, which is already 20, 27 minus 20, which is 7. And if you use the same trick, you just say, what is y? Y is going to be semi-perimeter minus x plus z, which is 18. So y is equal to 27 minus the 18, because that would be the x plus z. And that's equal to 9. And then z is the semi-perimeter 27 minus the x plus y, which is 16. And that's equal to 11. Now, whenever I do this, I always go and try to double check to make sure I didn't mess up. I don't like putting down answers and finding out later that they were wrong. Okay? So if I have 7, 9, and 11, what's 7 plus 9? That's equal to 16. Good. 7 plus 11 is 18. Good. And 9 plus 11 is 20. Good. So it all works. And then I also sometimes look at this and say, that's cute. 7, 9, and 11 are equally spaced. Did I expect that? Would you have expected the answers x, y, and z for the radii to be equally spaced? I always like to look at things and say, could I explain the pattern I see? And if so, I'm more likely to be correct. Can anyone think of why they should be equally spaced? Why should the x, y, and z be equally spaced? Is there anything about the numbers? Exactly. The side lengths that came in, 16, 18, and 20, were also equally spaced. And if you look at how we did this, when those three are equally spaced, those are the three things that I subtracted from the same number. So I had the same number, and I subtracted these three equally spaced things. And that was nice. Oh, and somebody also saw a pattern, which is that, look, this 9 here, this is exactly half of the average of the three. But that also makes sense, because if they're equally spaced, then the average of x, y, and z is the sum of the three, the average of the x, y, and z should be exactly half. What's the easiest way of thinking of this? All right, let me try to think of a good reason why it should be exactly half of the average of those. Somehow, to me, it's like because of the perimeter and the semi-perimeter. It's that, yes, the average of these three things is 2 times the x plus y plus z all over 3. And the average of the x, y, and z is just 1 times x plus y plus z over 3. So that's why it should be off by a factor of 2. Okay, that was actually kind of fun. So I was originally not really sure whether this would be an easy or a hard problem, but I just thought it looked neat. So many circles and a triangle. I just wanted to know the answer. Okay, what else can we talk about? Sophie Chang asked, how long did it take for you to code the program for this live stream? You mean the thing that I used to draw all these notes on? Well, again, I used Linux. In Linux, other people already wrote most of the code. So this thing probably has like thousands, if not tens of thousands of lines of code in it, of which I wrote almost none of them. I think I basically spent like an afternoon going and reading their code and finding out the places that I wanted to make changes. Because this particular program was not designed for this kind of a show. This program was designed for you just to be able to take notes. I'm not sure if any of you have these Microsoft Surfaces, or there's some program called OneNote. I'm not sure if you've seen this program before, like OneNote, where you can kind of draw on your computer and take notes. So that's the Windows version. And effectively, what there is on Linux is there's a free open sourced version where you have all the source code for the same thing as the OneNote. So I just went and took that thing and I basically said, I don't want all these crazy menus everywhere. I don't want all these other options. I just want something really simple where I can just click on a little palette here. And when I click on the palette, then I can, choose a color to draw on. So I just made some very small changes. Only took me like an afternoon. Okay, what else can we do? Oh my goodness. You guys are so funny. So Efren Zhao asked, pick any number. Okay, Efren Zhao wants me to do something insane. So he says, oh, it's great. And even better, whether it's a he or she, Efren Zhao has some very interesting initials. Efren Zhao says, let's do this easy problem, okay? Easy problem. You pick any number. Pick any number. Okay? And then we'll just do two things. Well, not two things. We have two options that we do. If it's even, then you divide it by 2. If it's odd, so there's these two choices. If it's even, divide by 2. If it's odd, just multiply it by 3 and then add 1. Does this make sense? Very simple thing that you do. And easy says, come on, there's something really easy and really obvious. Just please prove you always get to 1. Huh. You know, like, let's try. Does it work? Let's just choose a number and try. What's a nice number? How about 9? 9's a nice number. Is it even? No. So I have to do times 3 plus 1. Times 3 is 27 plus 1 gets you to 28. 28, I can divide that by 2. It's even, so I divide by 2, get 14. And 14 is even, so I can divide by 2, I get 7. Oh, 7's odd. I can't divide by 2 anymore. Times 3 plus 1, 22. Now I can divide by 2 to get 11. Okay, and now I have 11 times 3 plus 1 is 34. Hopefully I didn't make a mistake. 34, I can divide by 2, get 17. Oh no, I need to times 3 plus 1. What's that? Is it 52? I think so. Okay, I can divide by 2, that's 26. I can divide by 2, that's 13. Oh no, times 3 plus 1, 40. Okay, I can divide by 2 a bunch of times, 20, 10, 5. It's odd, so I need to times 3 plus 1. We're finally going to get there. 16, 8, 4, 2, 1. Okay, and so the question says, just prove this always works. How hard could this be? There's a problem. There's a problem in that you asked me this easy problem. This is a very, very, very famous hard problem. Nobody in the entire world knows how to prove this. This is called the Collatz conjecture. I saw that was already posted in the chat. This is a Collatz conjecture, and somehow, I chose 9. 9 is a very bad one. You put 9, it goes like, whoa, it gets bigger, bigger, smaller, bigger, smaller, bigger, smaller, and eventually it stops. But unfortunately, this is just not known, and in fact, many mathematicians enjoy thinking about this to try to figure out what the answer is. We don't know. We don't know how to do this, and I don't know how either. But it's a fun problem. Isn't it a millennium problem or something? Well, it isn't a millennium problem. You will not get $1 million for solving this problem. On the other hand, you will get extremely famous. So with all of these famous problems out there, it just happens to be that some of them happen to have these prizes. Others are just known to be very hard and you'll be famous. But you don't do a problem for the prize anyway. You do it for the fame, I guess. I see that somebody here made a comment. Why did you go and take the hardest problem of the entire live stream and put it as easy? Well, that's because the initials of the person who asked it were easy, and I thought that would be fitting for the most not easy question that we had today. Okay, more questions. Oh, I see. Colin Z, if you know how to draw an icosahedron, do you know how to draw an icosahedron? Oh, you want to draw a 21 sides thing. Oh, you're trying to draw a 21-sided shape. I don't exactly know how you draw a 21-sided shape. I'm a little bit afraid because the 21 is a multiple of 7. So I'm a little bit worried that it would be hard to actually draw with a ruler and a compass a 21-sided shape. But I will admit my memory, well, not memory is the wrong word, but I haven't used this abstract algebra in a while. What I'm referring to is that there are some shapes that you can draw with a compass and a straight edge. Like the compass, the thing you poke into the paper and you draw a circle. And there are ways to draw certain shapes if the only thing you have is a straight edge and this thing. And you can draw triangles, equilateral triangles with that. You can draw squares with that. But it turns out that there are some shapes that you cannot construct nicely. I'm a little bit worried that the 21-sided one might be one of those. And in that case, I wouldn't be able to do it. It's like this famous problem called trisecting the angle. It's actually not possible to use a compass and a straight edge to go and take, if somebody just gave you an angle, it's very hard for you to kind of do some random motions and cut the angle into 3 parts. Where when I say hard, it's actually impossible. Okay, what other questions do we have? Oh no, Ellen Way said that your school banned compasses because the pointy thing is a weapon. I guess you do need to be careful of those compasses. I used to take people to the International Math Olympiad and other competitions, and whenever we went through the airport security, we were always a little bit wondering whether or not people's compasses would get confiscated. Because you see, if you do math at the level of the International Math Olympiad, you need to draw really good pictures. The better picture you draw, the more interesting coincidences you can see. And so some people actually had some pretty fancy compasses. Like some compasses you can get like borrowing in school are like completely made of plastic, and they just kind of, you poke the thing down there, you start to draw the circle, and before you know it, the thing you poked has moved also. So it's not a circle, it looks like a lump instead. But then with the International Math Olympiad, people decided that they wanted to bring like architect compasses, which have like really good spikes. And then the problem with that is you go and bring it through the airport security and people say, what exactly do you have? And it's hard because, on the way out of the country, where you're going from the United States to the International Math Olympiad, it's hard enough because you've got these weird spikes. On the way back, what usually happens is that Team USA has also won some medals. And in the X-ray detector and the airport, what they see is they both see these compasses with the spikes, and they see these solid circular objects, which are like blocking the X-ray. And they say, well, what are you guys? Are you guys some crazy people or something? You have spiky things and you have these mysterious opaque discs. Oh, they're medals. Anyway, so that was a lot of fun. I mean, when I say that was a lot of fun, that was not a long time ago, but back when we could travel to international contests. We'll do our best to bring ourselves that world back as soon as possible. Okay. Wow. So unfortunately, it looks like we have actually hit the 5 o'clock time. So I'm sorry that somehow today it seems like there might have been some lag. I myself also noticed that there was some lag. Maybe the world happens to be watching YouTube for some reason. But if you were new on today's YouTube live stream, I'll say I hope you had an interesting time. Every single time we'll talk about a different subject. And in fact, this is the first time that we went and played with different kinds of infinity. What will we talk about tomorrow? I have no idea. But there's only one way to find out. Come join us, and I'll see you tomorrow.